what do we mean by cache memory? Now, cache memory is a memory that sits between the CPU and the RAM. Now, the RAM is good, but the problem with RAM is it is slower than the CPU. Inside the CPU, we have the registers. Inside the CPU, we have the registers. Now, these registers, the problem with the registers are they are few in number. So we cannot use them to store everything. So instead, we inserted a cache memory between the RAM and the CPU. Now, the cache memory is a small amount of fast memory. Now, when we talk about how small, we are going to talk about it later on. It sits between the main memory and the CPU, and it may be located on the CPU module. Yani, if I check here my computer, the one I'm using now, if you can see here, you can see that here I'm using cache. See the cache? I have 3 levels of cache. Level 1 is 256 kilobytes, level 2 is 1 megabytes, and level 3 is 6 megabytes. So I have 3 levels of cache. These cache memories are different in size. If you go back to the memory hierarchy over here, you can see that the cache is also has levels. Level 1 will be faster than level 2, and level 2 will be faster than level 3. But level 1 will be smaller than level 2, and level 2 will be smaller compared to level 3. Now, cache operation, when the CPU requests the contents of memory location, عادة, when we want a memory, we will go to the RAM and go to that memory location and get the information and send it to the CPU. Now, the problem with this, it is too slow. So instead, we do what? We go and we check the cache. Okay, we check the cache memory. Okay, we check the cache memory for that information. If the information is available from the cache, okay, if the information is available in the cache, then we take it from the cache. So, check the cache for the data. If present, meaning if the data is available in the cache, get it from the cache. If not present, read the required block from the main memory to cache. طيب, when we take information from the RAM to the cache, we don't take one memory location. Instead, we take a block of information and we save that information into the cache. ليش؟ لأنه usually if you use one memory location, you will need the rest of the block most probably to be used. This makes things faster. Instead of reading one location at a time, I read a block at a time. I will take that block and put it into the cache. Now, the block is saved in one cache line. So the cache has different structure when it comes to the building compared to the other CPU components. Now, so we read a memory block from the main memory and put it into the cache, then deliver from the cache to CPU. يعني, in other words, there is no direct connection between the RAM and the CPU. There is no direct connection between the RAM and the CPU. What we have is the cache sitting in the middle. We have the cache sitting in the middle. So the cache includes tags to identify which block of the main memory in each cache slot. Now, this is the flow chart. This is the flow chart that shows the operation of the cache. So we start at this point, receive address from register address from the CPU. Now, is block containing the register address, required address, available in the cache? If yes, take from the cache and send to the CPU. If no, access the main memory اللي هو الرام and get the full block containing the required address. Locate a cache line for the block, and then send the information to the CPU and load the memory block in the cache line. A cache design is a little bit different. When it comes to cache, a RAM, usually we draw the RAM something like this, and we say each RAM line or each location will have one information. But the cache is totally different. One cache line, okay, one cache line can hold one full memory block. So if I have a block of 1, 2, 3, 4, 5 locations, these locations will be put into the cache. These locations will be put into one line inside the cache memory. Yani one line inside the cache will hold one memory block. Now, how do we deal with this? We are going to discuss today. So first, the cache design. We need to know the size of the cache. What is the mapping function? And what do we mean by mapping function? What is the replacement algorithm? What is the write policy? What is the block size? And how many caches do we have? Like in this computer, we have 3 caches. So we have 3 levels of cache. Okay. So the size of the cache does matter. In terms of cost, more cache is expensive. In terms of speed, more cache is faster up to a certain point. Of course, you cannot make your cache very big. Then we need to check the cache for the data time to access it. Now this needs some time. Yani, the idea is instead of if there was no cache, then I will go and access the information from the RAM immediately. But if there is cache, first I need to check the cache. If the cache does not have the information, then I need to get it from the RAM. This will add some extra time. But on the long run, when you access all the block and you have all the blocks of information available in the cache, this will be a little bit more faster. So basically, this is my cache sitting between the processor and the bus, where we have the RAM somewhere around here. This is my RAM. My RAM is connected through the system bus. So first of all, the CPU will request the information. It will put the address on the address bus. Now, once the address is on the address bus, first we check the cache. Is the information available in the cache? If yes, the cache will put it onto the data bus. If not, the address will be forwarded to the RAM. The RAM will put the information onto the data bus. The data bus will put the information into the cache, and then from the cache, once more, we will put it back, give it back to the CPU. Now, how did this all develop? If you see over here, we have different types of computers. In 1968, we had the mainframe. It had only one L1 cache. Then we had in 1975, we have one L1 cache, but the size is 1 kilobyte. In 1993, where we started having the Pentium, we started having the level 2 cache. Then in PC server in 1999, we started having the level 3 cache. See, it's 32 kilo, 256 to 2 megabytes. And up till now, almost the same idea, we have 3 levels of cache. In this computer, as I showed you earlier, we have 3 levels of cache associated with this computer. Now, the mapping function. The mapping function is how do we access the data in cache. Remember, in the RAM, it was quite simple. In the RAM, you get one address, and that address will be used to access that memory location. When it comes to the cache, on the other hand, the cache is a little bit different because you have different mapping functions. So what is the mapping function? We have, let's say, a cache of 64 kilobytes. So each cache block is 4 bytes. So the cache is 64 kilobytes lines of 4 bytes. يعني الكاش has from 0, 1 up to 6, 5, 5, 3, 5 locations, which is 64 kilobytes. Or I'm sorry, it's not like that. It's not like that, because let me do the calculations, show you first. We have 64, okay, we have 64 kilobytes. Okay, we have 64 kilobytes. 64 kilobytes is what? 64 kilobytes is a kilo 2 to the power 10, with 64 is 2 to the power 8, 6, sorry, 2 to the power 6, so that's 2 to the power 16. Now 2 to the power 16 is basically divided into the cache is, since we have 4 bytes in each block, so 4 bytes is 2 to the power 2. So to get 2 to the power 16, we get multiply 2 to the power 14. So over here we will have 2 to the power 14 is 16 kilo lines, and each line can hold 4 bytes. So over here each line will hold 4 different bytes, and in total we have 2 to the power 16 lines. 2 to the power 16, sorry, 2 to the power 14. 2 to the power 14 lines, which is 16 kilo lines. So the number of lines is different. If we talked about this as a RAM, we will say 2 to the power 16. But here we have blocks of information. The access of blocks of information okay, so the values of each block is depending on the memory line that we are getting the information. So if I have 16 megabytes of main memory, يعني الرام is 16 megabytes. 16 megabytes is 2 to the power 4 multiplied by 2 to the power 20. Mega 20, that's 2 to the power 24. So we have 24 address lines. How do we map 16 megabytes to 16 kilo lines? This is the question. And this is what we are going to talk about, which is the mapping function. So what happens is, this is my RAM, and this is a memory block, as you can see over here. This memory block contains k number of words. These k number of words will be mapped to this cache line. هذول كلهم. So the length of this block is k words. You can see here it is k words from here. So these, let's say these are 5 or 6, will be put over here in this line. The next block will be put in this line. The next block will be put in the third line, and so on, until we reach the maximum number of blocks that can be saved in the cache. Along with that, each block will have a tag. So we have a line number, and we have a tag. I will explain why later. So one method of mapping is called the direct mapping method. In the direct mapping method, each block of main memory maps to only one cache line. يعني this block can only be found in this line. The next block can only be found in this line. طيب إذا كان عندي أنا 16 megabytes and here I have only 16 kilo lines, how I will do it? So the idea is, if you want this block of data, you are going to search for it here and only here. This will reduce the time of finding the information. If it's available in that location, good. If not, bring it and put it in that location. It's easy to understand. If I want to know where someone is, instead of searching, I will go to a particular place and find that data instead of searching. So the address, if a block is in the cache, it must be in one specific place. Now, the address is two parts. The least significant W bits identify a unique word. The most significant S bits specify one memory block. The most significant bits are split into cache line field, which is R, and a tag, which is S minus R, where S is the memory block. In other words, this is the whole thing. So the tag is S minus R. So then we have R, which is the cache line, S is the memory block, and W is the word identifier. لما الword identifier يكون 2 معناته this is divided into 4 blocks. So we have 24-bit addresses. 24-bit addresses. 2 bits are for the identifier. معناته عندنا 4-byte block. ليش 2? 2 to the power 2 is 4. 2 to the power 2 will give you 4. معناته this can be divided into 4. Then we have من ال 24, these are 24, راح منهم 2, we are left with 22 lines. هذول 22 lines are the block identifier. The most significant bits are called the tag, and the least are the 14-bit slot or line. Now, no two blocks have the same tag field. No two blocks, remember each block is 8 bits. No two blocks will have the same tag. Each block will have a different tag. We can check the contents of the cache by finding the line and checking the tag. So we need to find the tag and we need to check the line for the information. So this is an example. If we are talking about cache 0, cache line 0, which is this cache over here, this line can hold the blocks 0, M, 2M, 3M, up to 2M, 2S minus M. If we are checking the line number 1, then it will be holding memory block 1, M plus 1, and so on, until the end of the cache lines. يعني each block over here can hold only certain parts of the memory. يعني مش أي block بتجيبه بتحطه في الline. Each block can hold a certain part of the memory, and this is basically to keep things in the right context and make sure that you find your information much more faster. إذا information you are searching for it, you find it in the place where it's supposed to be, you are going to find it fast. If it's not available, then you will need to fetch it from the main memory. فمثلا, you can see here that this is a mapped organization of the cache, and you can see here that this is my cache having a tag, and each tag will have a block of information inside it. Now this block will be mapped over here, this block will be mapped over here, and then we try to find the information through the cache. This is just a block diagram of how the cache operates, Again, this is your main memory of 16 megabytes, and this is your cache. You can see that the first block of data from 00 to 04 will be mapped to line 0. Also, the first block of data of this second part of the main memory, لأنه المين memory قسمناها, will be also mapped over here, and so on. So this is basically how it is done inside the cache memory. However, it's much more complicated, but I just want you to get the idea. It's not the end of the memories. We still have more memories inside the computer that serve as part of the memory systems between the cache and the RAM. Now, the direct mapping, which we talked about, it has some pros and cons. Pros, advantages, cons, disadvantages. So the pros and cons, it is simple, it is inexpensive, يعني it is cheap, but it has some problem that it has fixed location for giving blocks. If a program accesses 2 blocks that are mapped to the same line, the cache misses are very high. يعني if we try to access 2 blocks, okay, if we try to access 2 blocks that are supposed to be mapped to this line, then every time we want to access, we need to get the information from the main memory. This will give the misses very high. misses اللي هم الأخطاء. في عندك إشي اسمه cache hit and cache miss. Cache hit means that you are getting the information every time. يعني you are getting your result every time. الcache miss means that you are missing the information. تعرفوا hit and miss. Hit معناته جبت الهدف, miss معناته أخطأت الهدف. Now, how do we replace the data inside the cache? يعني جبت الداتا, I put it inside the cache. Then the next step is I want to replace the data inside the cache. In order to replace the data inside the cache, I need to use replacement algorithms. One of the replacement algorithms used is the hardware implemented algorithm, which is fast. Then we have least recently used, يعني أقل information used, we will replace it. We have another method which is first in, first out. أقدم information inside the cache will be removed. The oldest, which is the first in, first out. Least frequently used. نحسب كم مرة استخدمنا الميموريز. أقل واحد تم استخدامه بعدد التكرار. يعني كم مرة استخدمت اللاين الأول, كم مرة استخدمت اللاين الثاني, كم مرة استخدمت اللاين الثالث. بعدد التكرار, the least frequently used. So replace the block that has fewest hits. And finally, we have the random, which we randomly remove information from the cache. The Pentium 4 cache, if you go back to the history, you will find that 386 has no cache on chip. The 486 used 16 kilobytes of line 4-way associative organization. بعدين اجى عندنا البنتيوم. البنتيوم used L1, 2 L1 caches, one for data and one for instructions. يعني البنتيوم it used 2 on-chip L1 caches. The Pentium 3, on the other hand, used L3 caches, level 3 caches. The Pentium 4, it used L1 cache, L2 cache, and L3 cache. The L1 caches were 8 kilobytes, 64 byte lines, and 4-way associative. The L2 cache was feeding both the L1 cache caches. ليش؟ لأنه L1 كان عندنا 2 caches, واحد للداتا وواحد للinstructions. Then we had an L3 cache. التطور تبعتهم. How did we get to this level? It started from the information over here. البروبلم بلشت قبل 386. external memory is slower than the system bus. external memory RAM. add external cache using faster memory technology. ففي ال 386 we had an external memory outside the CPU. بعدين they said okay, increase the processor speed results in external bus becoming a bottleneck. البوتلنيك اللي هو عنق الزجاجة. When you have a lot of information and it is passing through one place, you will have a congestion. So عندك زي زحمة. Okay, this bottleneck is a problem. So they said okay, before 86 move the external cache on chip. move اخذ الكاش اللي كان external على المذر بورد وحطه داخل CPU. So this is the 486. With 386 there was no on chip cache. With 486 they put the cache inside the CPU. بعدين they said internal cache is rather small due to limited cache space. They added an L2 cache outside the memory. فبال 486 صار عندنا ال L1 cache inside the processor and the L2 cache was outside the processor. فصار عندنا 2 caches. بعدين اجى عندنا البنتيوم. في البنتيوم المشكله بلشت انه contention occurs when both instruction prefetch and the execution unit simultaneously require access to the cache. In that case, the prefetcher is stalled while the execution unit accesses the data. فقال لك شو الحل؟ Create 2 separate caches, one for data and one for instructions. في البنتيوم. بعدين في البنتيوم برو increase the processor speed results in external bus becoming a bottleneck اللي هو for L2 cache. طيب الحل create a separate backside bus that runs higher speed with the main bus. This is the backside bus. It's called BSB. is dedicated for L2 cache. وبعدين move L2 cache into the processor. ففي البنتيوم برو عملوا بس خاص في الكاش وفي البنتيوم 2 قال لك لا move ال L2 cache inside the processor. في البنتيوم 3 they added a level 3 cache وفي البنتيوم 4 they added the level 3 cache onto the chip. الكمبيوتر اللي بنستخدمه حاليا it has 3 levels of cache and all of them are inside the CPU. Finally, this is the block diagram of the Pentium 4. You can see this is the L1 data cache and this is the L1 instruction cache. Then we have the L2 cache and the L3 cache. We have L2, L3 and L1 caches, all of them inside the CPU, and this is how your CPU will look like. This is your ALUs, this is your storage units, and this is basically how it is done. Now, الفكرة, okay, the idea is, let me show you, okay, before I finish up, okay, we have something called the Optane memory. The Optane memory, basically, the Optane memory sits between the cache, and the RAM also. This is a new memory. Watch this video and see how it operates.
Understanding Intel Optane memory is as easy as, well, making pancakes. Don't believe us? Start by thinking of the data your computer uses as the ingredients you need to make pancakes. Imagine the computer's processor as the cook and the DRAM as the kitchen countertops. The store that sells all these ingredients is the hard drive, and it's a mega store 2 towns away. To get the ingredients, the cook has to drive to the store and bring the ingredients back to the countertop where they're needed to cook. That's a lot of work every time you want to make pancakes. Until now, speeding up this process has usually meant adding more DRAM, or counter space, but that is both expensive and unrealistic. Even with a larger, expensive countertop, you still need to get all those ingredients from the store. That's where Intel comes in. Intel Optane memory sits between your hard drive and your processor, kind of like a big, convenient pantry right next to your kitchen. Intel Optane memory also uses a system accelerator driver. Let's call this driver your sous chef. The sous chef gets everything ready for the cook. Over time, your sous chef learns that you make pancakes every Saturday morning. Good for you. To prepare, our awesome sous chef gets the ingredients you need from the store and keeps them in the pantry. So the system accelerator automatically learns your computing behaviors and accelerates frequent tasks by intelligently identifying the files and data you access most frequently and storing them in the Intel Optane memory module. Thank you, sous chef. Now you have all the ingredients or data right where you need it in your pantry. So no more trips to the store. It's a faster, more responsive PC with no lag. Intel Optane memory will accelerate any 7th gen core processor-based system. How do you get Intel Optane memory? Install the Intel Optane memory module in an Intel Optane ready motherboard or system. Or, beginning this summer, purchase a complete system with Intel Optane memory already installed from a local retailer, so you can be a beast in the kitchen and achieve dramatically better performance with all the storage capacity you need. In other words, you can have your pancakes and eat them too. For more information, go to intel.com/optane.
So this is basically an Optane memory, which is a new type of memory. This memory is trying to make things faster. The information, the main source of information is your hard drive. The hard drive is then connected to the RAM. The RAM is connected to the cache. The cache is connected to the registers inside the CPU. The problem is the RAM is much more faster than the hard drive, so they put this Optane memory. الأوبتين memory تيجي على شكل solid state drive M.2 NVMe drive, and this Optane memory will operate as a secondary RAM. It will have the information for the RAM ready much more faster than the hard drive. Technology is developing. That's basically just I wanted to tell you how things are operating now. Okay, so what we have left is basically next class we are going to talk about the RAM and ROM design. In the lab, you are going to continue your design with Miss Alia. Tutorials I have already uploaded for you, and extra videos are there on SULMS to help you through this module. We still have 6 weeks to finish. The material I have uploaded the material for the rest of the semester, so you can download all to the end of the semester. Everything is ready on SULMS. Do you have any questions before I leave?
لو سمحت